Merci bien, Roger. C'est plus efficace, je crois, si je parle en anglais pour ces derniers diapositives. Désolé pour ça. So I'll speak about two British projects that we've been involved with in my group at Imperial College. The first concerns piles driven in chalk, that's battu et lacré, and then talk about the Pisa project with monopiles driven in sand and clay. So the work on chalk has been motivated by large offshore wind farms. This is one off the German coast in the Baltic, at a place called Wikinger, which is German for Viking. And there'll be 70 jacket structures with 286 piles, and they're large piles that will found these multipod structures. They're now installed, and there was concern over the chalk at this site, considerable uncertainty for design, and this was met by performing at full scale in the field static, cyclic and dynamic testing, and we advised on that and took part in that project. And we also ran a parallel research project in the UK, which we've just recently finished. So this was a joint industry project, and the partners were Innovate UK, Imperial College London, where I work, Iberdrola and their subsidiary, Scottish Power Renewable, and GCG, which is a small consulting firm in South Kensington in London, where I work. So our two research sites were first of all in the German Baltic, here between the islands of Bornholm and Rügen, and there testing was carried out at the bottom of the sea in 40 metres of water. And that included static, cyclic and dynamic testing. And this is in low to medium density chalk, for which there is considerable uncertainty about the axial or the lateral behaviour of piles. The chalk is overlain by glacial till, moraine, and that was also a factor in the investigations there. Then we moved closer to my base here, to Kent, in southeast England, where we had a former quarry, a carrier, and there we did testing with reduced scale, more control, and there again we worked with low to medium density chalk, but this time running straight to the ground surface. Now the offshore testing was carried out with a rig of this size. You can see here a person for scale, but nobody was involved in this. The testing was completely operated robotically, remotely from the seabed. And the testing was carried out at 3 turbine locations where there were different degrees of moraine till over the chalk. The Kent test site involved far smaller piles, but this was something we could do from a university budget, driven piles with dynamic monitoring. We also worked with the ICP. You saw the small version of this used in Grenoble. Many people have shown the interface stress paths today from the smaller version. This is the larger version that we originally used, for example, in La Benne with our président, published together 20-something years ago. And of course, here we also did in situ testing and laboratory testing. So the profile in the Kent site, to give you some idea, cone resistance, typically 10 to 30 megapascals, but with some silica bands of what we call flint in English. And here the water table was below the level of investigation, but the chalk was still saturated and medium dense all the way from the ground surface. So you can see here the industrial scale piling. Here's a person for scale. For the steel piles that we drove at this site, dynamic monitoring was instrumented. And our first area of interest was the effect of age on the piles driven in chalk. Elizabeth just mentioned the Syria codes. In the Syria codes, there's no mention of pile age. It turns out to be as important as any other factor. In fact, maybe even more important than chalk density is age. Also, in the Syria code, there's no guidance over cyclic loading, but some people are very worried that chalk will have terrible performance under cyclic loading. It's well known that you can destroy chalk to a putty to make it like a soft clay with cyclic loading. Will that work against these piles? We also wanted to try and get the same insights we've seen today from the Grenoble tests with our mini ICP. So we used the larger ICP at St Nicholas at the Kent site to complement the driven piles. They're not that big, 100 millimetre diameter, but we can measure the local radial and shear stresses, pore pressures and axial loads on this pile. And we can study what happens during installation, long-term equalization and loading. And we called back Barry Lahan, who worked also with Roger and I originally for his PhD. He's a professor now, but for his PhD he worked in La Benne with this equipment and elsewhere. Now the results are still confidential, but I will give you a flavour of them. They're going to be published in a few months. So first of all, stage loading tests, axial loading, and the local effective stress paths. The stress path response is similar to that we see in sand, constrained dilation and modest interface shear angles. No cohesion. So we can measure those effective stress paths during static loading and cyclic loading, and we see this constrained dilation much as the same as Fauré and Boulan postulated for sand back in the 80s. And we can also see what happens under cyclic loading. The most important factor, though, for static capacity is age. This should be 1 here. This is our end of driving static capacity. It increases by a factor of about 6 over 250 days. Very important setup in chalk. Massively important. So someone who does pile driving monitoring and then moves to predict static capacity from that will be very conservative indeed, unless they wait for a long time. If you retest the same pile, just as we showed at Dunkirk about 20 years ago, you don't have the same response. Each pile should be a virgin pile at the time of testing if you want to demonstrate the aging without having confusion. And we also did laboratory studies on the ground around the piles. With the driven piles, we did static testing and also cyclic testing. Here you see the program of cyclic tests. We've seen this diagram many times today. These are our 7 cyclic experiments. First, we did a reference test, as everyone has discussed, and then we performed our experiments on 4 piles that were reserved only for cyclic loading that had no prior loading, and this was all done 250 days after driving. We tested these with cycles of about 20 seconds periods and up to 1,000 cycles with some simple equipment that we made ourselves and designed at Imperial College. It was quite inexpensive. To give you a feeling for the results, as we've seen with sands and clays, we can have some combinations which are unstable and fail within just a few cycles, and other combinations where we can cycle for 1,000 cycles and have less than 1 millimetre of movement. So we have stable, unstable, and in between some metastable results. So all 3 types of response are observed, reference back to static failure, and what appears from this is the chalk is not massively unstable under cyclic loading. Not fantastically different from the clays or the sands we've seen today. What we'd like to do now is some larger tests, and there are 2 or 3 people in the audience who we hope will join us in a new program, which we call Alpaca, friendly animal from the Andes, and this will involve larger tests, we hope, at the same site, which will be instrumented much in the same way that Elizabeth was discussing just now. So in summary, for the chalk, we have tests offshore, static, cyclic, dynamic. We have them onshore too, instrument of the local stresses. All of this was completed in 2016, and we're now moving towards new pile design methods for chalk, for driven piles. There will be papers in the SUT conference this September in London. One paper is accepted by Geotechnique now and will appear fairly shortly. There's another one which we hope will be accepted by the Canadian Journal, which is under review at the moment. Further work in the Alpaca program with lateral loading and larger piles. And again, we are learning, just as we've heard from Elizabeth, from the PISA program that we've been involved with, which concerned monopiles, monopure. So to move to the PISA program, PISA involved many more partners, including, for example, EDF here. It was led by Dong Energy from Copenhagen, and it had an academic research group or work group of Oxford, Imperial College and University College Dublin. And actually there were 4 or 5 of us from Imperial College who were involved in this. And the programme was conducted over 2-3 years and is now completed. So all the reports are written and it remains confidential for a few more weeks, I believe. So the main aim in the PISA programme was to look at monopiles with low L upon D ratios, caissons in effect. Now, if we consider a conventional PY analysis, as we've heard today from many people, we'll be developing lateral resistance in this way. And if we move to use, for example, the standard international offshore approaches from DNV, ISO, or API, we have very little scope to capture the detailed soil properties. Very few soil properties go into these PY curves, and we'll see the consequence of that in my last slide, or last slides. In PISA, we wanted to do better than this and optimize caisson design. Firstly, we have a large overhead moment in monopiles, big horizontal forces, and with a short length compared to diameter, we pick up other important force components. At the base, a shear force and a shear moment, or a rotation moment, and along the sides of the pile, we have distributed shear stresses. These all affect the response of the pile. Now, the aim in PISA is to come up with new ways of describing these springs, all 4 components now, not just the lateral PY component, and also to be able to tune these to site-specific soil properties. And that has been done on the basis of advanced finite element modelling, and that process has been checked by tests on 28 driven steel piles at 2 sites, one in France at Dunkirk and the other one in the UK in Cowden. Dunkirk sand we know. Cowden is glacial till, moraine, and it's a stiff, low plasticity clay. So the testing looks like this. We have reaction piles, we have test piles, we have pile diameters up to 2 meters, we have a range of length upon diameter ratios, we have a range of eccentricities of loading, and a range of wall thicknesses. The tests involve static testing to failure, which is the main focus to improve the static TY, but also cyclic tests and rate testing, 14 tests at each site, including actually more than that if you count all of the cyclic tests. And the piles are instrumented with the first ever fibre optic use, surviving driving, as we just heard again for the limestone here in France, inclinometers displacements, and also pore water pressures. Comprehensive in situ testing, and also a big program of laboratory research. And this was probably my main element, was to supervise 2 PhDs, testing again Dunkirk sand, static and cyclic, and Cowden till from Humberside. The till, a moraine, poses many problems. It contains beaucoup de cailloux, comme ça, and that makes a problem, especially when you want to test with a hollow cylinder, cylindre creux. It's a nightmare to make hollow cylinder samples from this, but we did it. I had a very patient Chinese student. For every 1 test that succeeded, 5 failed, but we completed his program. So to help this, we did CT scanning of our cores, and we mapped out with image analysis the cores. So the kind of testing that they did was to use highly instrumented triaxial cells with multiple axis body wave measurements, high resolution local strains, local pore pressure, and also hollow cylinder experiments with a complete program on that horrible till. From this, we had all the parameters we needed for the modeling: compressibility, nonlinear stiffness, and shear strength. We could also characterize anisotropy, strain rate, and cyclic dependency in the 2 soils. The modeling, I will only talk about the modeling for static in the next couple of slides. For Cowden, the Imperial College Finite Element Program, ICFEP, was used for all the modeling, and this had an expanded modified CAM clay model within it that could deal with nonlinear stiffness, deal with effects of overconsolidation ratio. For Dunkirk, a bounding surface plasticity model was used, which dealt with strength variation in the deviatoric plane, effects of densities. And to give you an idea of the number of people involved, this is the list from the first of the papers that describe this work. Many people, including, for example, Guy Holsby and others who made contributions to this work. So let me show you what the testing looks like. Here we have it. Aha, my cyclic test didn't show here. It checked when we tested it before. Anyway, we can try. We should have put it in a file. It's okay, never mind. It's okay. We have a big cyclic test underway here at Dunkirk. I'm sorry the computing system didn't show it today. We checked, it showed earlier. But these are 2-meter diameter piles. In the background is the port of Dunkirk, and you can see these moving with large deformations under cyclic loading. 10 meters in the air, 10 meters of height for loading. So the question is then, does it work? Well, let's see first of all what the conventional procedures do compared to the measurements. Here is the conventional routine international design guidance, horizontal load against displacement. This is what we found in our tests. Actually, this is at Cowden in glacial till. Wrong by a factor of 3. And then if you see the new procedures coming from the numerical analysis and the PISA process, much better fit. So I think there's a long way to go before we can make really good predictions for these large eoliens. We think we have a new method in PISA. The method is being tried and is now being used in offshore design in a number of wind farms in the North Sea, the German Baltic. So it is in use, and we have hopefully a way forward which can be applicable to onshore foundations and caissons as well as offshore conditions. So in summary, for PISA, we're trying to improve the design of monopiles. Big emphasis on static response first, because that is not correct necessarily, and then cyclic to follow. Extensive analysis with advanced finite elements and field testing supported by laboratory testing. There are new design approaches which are now in use by the market leaders. They're using this already. And there are papers coming out. There's a keynote at the SUT OSIG, and there are journal submissions which will be made soon as well. There are 4 papers in preparation which are going to be going soon for review. And there's also a PISA 2 project which started a couple of weeks ago in Copenhagen. We went to the launch meetings there, where there'll be a wider range of soil conditions, looking at different types of clay in particular, and also different sand conditions. And the next new problem really is to see what we can do about cyclic design, and it'd be very interesting to see how the SOLCYP approach would work when compared with these big tests in Dunkirk. So thank you very much for your kind attention. That's my last slide.